Selamat sejahtera semua. Hari ini saya akan pembentanan teks 1 TC test of three-phase induction motor. My name is Teh Jing Kwan. My matric number is CE240040 daripada kod 7 section 1. Untuk part simulation test 1 TC test of three-phase induction motor, kita daripada kod 7 section 1. For kod 7, dalam bahagian acceleration machine, square theta PC model kita akan pilih 7, iaitu 200 HP, 460 watt, 60 Hz dan 1785 RPM. Lepas tu, dapat square open parameter, machine input adalah token, reference payment adalah loto. Lepas tu, kita akan color measurement, voltage measurement untuk keluar output VDC dan IDC. Lepas tu, ada continuous stage. Lepas tu, kita ada 5 watt DC, 3 resistor R1, R2, R3. Setiap resistor adalah 80 kilo ohm. Lepas tu kita akan run simulation second ni. Kita run untuk stop time kita setting akan 10 second. So sampai dia run sampai habis, sampai dia 10 second. So kita boleh nampak dia dalam setiap second nanti akan ubah dia punya IDC dan VDC. So kita nak gelakkan sampai dia stop 10 second, akhirnya dia dapat IDC dan VDC dapat berapa. Akhirnya kita stop 10 second, akhirnya kita dapat IDC adalah 139.8 ampere dan VDC adalah 5 volt. So VDC adalah sama dengan kita setting tadi 5 volt. Untuk part calculation test 1, lihat simulation daripada MyLab kita dapat IDC sama dengan 139.8 ampere, VDC sama dengan 5 watt. Untuk nak kira R1, basic R sama dengan VDC bagi IDC. Kita dapat R sama dengan 0.035765 ohm. Oleh sebab R measure ini adalah sama dengan 2 kali R. R1 tambah R1 sama dengan 2 R1. So, nak cari 1 R 1 berapa? So, kena R1 sama dengan yang tadi R measure bagi 2. So, akhirnya kita dapat R1 sama dengan 0.017887 ohm.
Assalamualaikum warahmatullahi ta'ala wabarakatuh. My name is Muhammad Zaim and I'm from Group 7. Today I will present about test 2 is block rotor test of three-phase induction motor. Our lecturer is Dr. Hisham and we from section 1. Okay, now I will show you our V nominal is 1. This is V nominal 1. Okay, and then our preset is preset 7. So because we from group 7, this is our preset. 200 horsepower and 460 volt and 60 hertz, and the RPM is 1785 RPM, and then we apply. Okay, now as you can see, I run it for 10 seconds. As you can see, for the V phase, we got like this is V phase and this is I phase. So as you can see in my report, wait now. So this is my report. So our voltage phase is 0.9999 and our I phase is 6.927 ampere, and our PSC is, our stator copper loss is 3.9 watt. So this is for test 1. Okay, next. And this is our calculation that I calculate. So if you can see, for the PCU stator and PCU rotor, I get for stator is 2.57 watt and for rotor is 1.4 watt. And then for the ISC is, I get the 1523.64 ampere, and for the V total V terminal is 1.7332 volt, and for the angle is 78.9, and I get the 0.144 for the Z impedance, and then I got the RLR and XLR. So because of that, we can calculate the value of R2 and X1 and X1 and X2. So therefore, this is the power factor. I got the power factor is 0.19. And then we go to the calculation for the VRMS2, V nominal 2. So I will set it as V2 right now. And I will run it. Okay, now as you can see, for the V phase I got 2. And for the I phase we got the 13.86 ampere, and for the watt is like 15.94 watt for the stator copper losses. And then our our torque is 0.02852 nano Newton per meter. So this is my calculation for V2. As you can see, there is a it's the same as the previous, but the only value that we change is 2. So right now, when we change to 2, the only different from this from the previous calculation is the value of stator and rotor. It changed over time. For the VT also different, and for the impedance, for the impedance same, ZLR is same, and for the angle also same. Yeah, and for the I for the IS and also same. The only difference is here is stator and rotor. Okay, and then next I will change it to 3. Yeah, and then I will run it. So as you can see, my field voltage is 3 right now because I set it to 3, and then my I phase is 20.7879 ampere, and for the stator copper losses is 35.8 watt right now. And then for the calculation, the difference also come from the PCU stator and rotor. Yeah, the only difference is stator and rotor. And for the VT also different because we need to convert V line, V phase to V line. So we can get the V line is 5 volt, 5.1996 volt. Alright, that's all from me, and the other group will continue my calculation, which is V4 and V5 from my friend. Thank you.
Hello, my name is Mr. Nixon and my ID matrix is CE240148. So today I'm going to explain for the task 2. The block rotor test was conducted at several applied voltage levels. The result and explanation for VRMS 1, 2, and 3 volts have already been discussed earlier by my teammate Zaim, including the current behavior and loss characteristic at the lower voltage condition. Therefore, in this part of the presentation, I will focus on specifically the result obtained at 4 VRMS and 5 VRMS. So, at 4 VRMS, the rotor remains completely stationary, giving a slip of 1. The applied phase voltage is approximately 3.999 volts, which produces a line phase current of 27.72 amperes. So under this block, the rotor condition, the input power is mainly dissipated as copper losses in the stator and rotor windings. So the stator copper loss recorded is 63.79 watts, and a small electromagnetic torque of 0.1156 Newton meters is generated due to the interaction between the stator magnetic field and the rotor current. So when the applied voltage is increased to 5 RMS, so the current increases proportionally to 34.65 amperes. As a result, the stator copper loss rises significantly to 99.67 watts, while the electromagnetic torque increases to 0.1806 Newton meters. Despite the increase in current and torque, the rotor speed remains at 0, confirming that the rotor is still fully blocked. So overall, the result at 4 VRMS and 5 VRMS shows consistent trends where the current, torque, copper losses increases proportional with voltage. This indicates that the lock rotor impedance remains nearly constant, validating the accuracy of the simulation. So these parameters are essential for determining the motor's starting characteristic and analyzing its performance under high slip conditions. So next, I will show the manual calculation for the 4 VRMS and 5 VRMS. So this is the value we obtained from the MATLAB just now, where for the rotor speed, phase voltage, and line current. So this is our manual calculation. So for this part, I will explain the manual calculation for the block rotor test. The maximum applied voltage is 4 volts based on the values obtained from the simulation. So from the simulation result, the phase voltage is 3.999 volts and the phase current 27.72 amperes. And the stator copper loss is 63.79 watts, Since the motor is connected, Y connected, the line current is equal to phase current, which is 27.72 amperes. So first, the current is scaled to the rated voltage of 220 volts to determine the equivalent short circuit current. Using proportional scaling, the currents become approximately 1524.98 amperes. So next, the input power under the block rotor condition is calculated using the stator copper loss equation. From this, power factor is obtained using the relationship between input power, voltage, and current. The calculated power factor is approximately 0.192, which is relatively low. So this low power factor is expected because during block rotor conditions, the leakage reactance dominates. After that, the lock rotor impedance is calculated using the ratio of phase voltage to phase current. So substitute the values. The impedance is approximately 0.144 ohms, and then using the impedance and power factor, the lock resistance is calculated as the real components of the impedance. So this gives value approximately 0.0277 ohms. The lock rotor reactance is then obtained from the imaginary component of the impedance is approximately 0.142 ohms. From the DC test, the stator resistance known to be 0.0178 ohms. By subtracting this value from the lock rotor resistance, the rotor resistance is obtained as approximately 0.0098 ohms. The total leakage reactance equally divided between the stator and the rotor, giving X1 and X2 values approximately 0.071 ohms each. So finally, the stator loss is calculated using the equation which gives approximately 41.22 watts. By subtracting this from the total copper loss, the rotor copper loss is obtained approximately 22.57 watts. So in conclusion, the manual calculation closely matched the simulation result, and the consistency of impedance, resistance, and reactance value confirm that the block rotor test has been performed correctly, and the extracted the parameters are reliable for motor performance analysis. So same goes to 5-RMS, where we calculate and we get the same value as we obtained in the MATLAB for the 5-RMS, which for the electromagnetic torque, rotor, phase voltage, line current, and stator copper losses. For the test tree, this test is comparable to the open circuit test performed on a transformer and is mainly used to obtain the shunt branch parameters of the induction motor equivalent circuit. So during the test, the motor was supplied with the rated voltage at rated frequency while no mechanical load was applied to the shaft. So under no load condition, the motor was allowed to run freely and the rotor speed increases until it reached a value very close to the synchronous speed. As a result, the slip became nearly zero, causing the rotor current to be extremely small. So this effectively makes the rotor circuit behave like an open circuit. So therefore, the input current drawn by the motor is mainly the magnetizing current required to establish the air gap flux, along with a small component to supply core losses and mechanical losses such as friction and windage. In the simulation, the stator terminals were connected to a three-phase supply at rated voltage, and mechanical load torque was set to the zero. Once steady-state operation was achieved, several parameters were recorded from the simulation. The phase voltage was observed to be approximately 212.3 volts, while the no-load line and the phase current were both measured as 63.03 amperes. The rotor speed reached approximately 1,800 revolutions per minute, which confirmed that the motor was operating near synchronous speed under no load condition. The electromagnetic torque produced was small as expected, since no external mechanical load was present. From the simulation data, the stator copper losses under no load condition were measured as 1,903 watts Further calculation were then performed to separate the loss components and determine the equivalent circuit parameters. The equivalent impedance of the motor was calculated to be 3.368 ohms, while the magnetizing reactance, which is XM, was obtained 3.297 ohms. So the stator copper loss at no load was calculated to be 213.132 watts, and the remaining input power was attributed to rotational losses. The rotational losses, which include core losses, friction, and windage losses, were calculated as 1,689.86 watts. So, in conclusion, the no-load test successful provided the necessary data to determine the magnetizing branch parameters of the three-phase induction motor. The results obtained are consistent with induction motor theory, where the magnetizing reactance is significantly larger than the leakage reactance, and most of the input power at no load is consumed by core and mechanical losses. This test plays an important role in completing the equivalent circuit model of the induction motor, which is later used for accurate performance analysis and torque speed characteristic simulation.
And today I will present test 4. Okay, now as you can see, this is our preset. And this is our parameter. Okay, we apply. And then this is our voltage, 460, and the frequency is 60 hertz. Alright, and then we run it. As you can see, the value we get is for electromagnetic torque is negative 4,300 68 negative 4,318. Value rotor speed 1,910, and then the value V line is 432.5 volt, and for the I line equal to I phase is 1,222, and for the value stator copper losses is 1.7222 megawatt. So as you can see, this is our graph where it peaked at the rotor speed is peaked at 1,678.2, and for the electromagnetic torque is 3,300 18.3 3318.3 for electromagnetic torque. For the rotor speed is 1,678.2 RPM. Okay, and this is our calculation. So as you can see, we get for the efficiency is 38.5534% for the efficient of this motor. So that's from me, and thank you.